The last topic is called the phase portraits. As you can see, this is our answer. Okay, x will be like a c times e to the at. So I have a time here. So since I have a time, I really want to know the shape, how the shape looks like. And because when t equals 0, where's the point? When t goes to infinity, how do they go? They will go to the infinity, or they shrink, or they converge. So that's why we have phase portraits of the homogeneous linear systems. So for the phase portraits, that means we need to sketch the trajectories. To sketch trajectories, which means to indicate direction of motion. And it's by arrows pointing in the direction of increasing t. So when t changes, how will this motion go? They will do like spiral going out, or the spiral going to the origin, or maybe it is just like exponential function, decayed, or the other way, go to infinity. So first, let's see, A is just 2 by 2. And if you take the advanced control theory or nonlinear, or even nonlinear control theory, you may also use this phase portrait. A is 2 by 2. And we assume that A is non-singular. So I have a trivial solution, x equals a 0 vector. Then we consider a homogeneous linear system, x prime equals ax. I also have initial values. We can find A using the matrix P and the diagonal matrix D. And what is P and D? This is your eigenvectors, and here this is eigenvalues. So we change variables. If we change variables from x to y, now if I can have x equals p times y, bring this back to the linear system. We're doing the same thing. P y prom equals x p d p inverse and x, so py. Again, this is x prom equals a x. We know y prom will become is the diagonal matrix times y. That means y1 prom, y2 prom is equal 2, lambda 1, 0, 0, lambda 2, y1, y2. Then y1 prime equals lambda 1, y1, y2 prime equals lambda 2, y2. So y1 c equals c1 e to the lambda 1t, and y2 c2 e to the lambda 2t. Then x equals p y. We know p is formed by your eigenvectors p1, p2, and your y, we just found that c1 e to the lambda 1t and c2 e to the lambda 2t. So that gives you c1 p1 e to the lambda 1t and the c2 p2 e to the lambda 2t. How do we get the coefficients c1 and c2? When t is 0, we have our initial value, which is x1 of 0, x2 of 0. That is c1 p1 plus c2 p2. And then in this equation we can get c1 c2. Now this is the equation, and I want to see the figure. Okay, from t equals 0 to t equals infinity, what is the shape or what is the trajectory of this x? And it really depends on the lambda 1 and lambda 2, right? E to the 5t, how do you plot this? Going up. E to the minus 5t, going down. And how about e to the 2 plus 3jt? Okay, let's see. I have two variables, lambda 1 and lambda 2, or two eigenvalues. We have some conditions or different types. First, when lambda 1 and lambda 2 are less than 0, e to the minus 5t, we can definitely expect they're going to 0. And also, these eigenvalues are real, negative, and different. So if they are different, for example, like minus 5 and minus 3, say lambda 1 equals minus 5, and lambda 2 equals minus 3. Then your x is c1 p1 e to the minus 5t plus c2 p2 e to the minus 3t. Take the common term outside, which is e to the minus 3t. Then we have c1 p1 e to the minus 2t plus c2 p2. Now we need to know or predict when t goes to infinity, what happens to this equation. When t goes to infinity, e to the minus 3t c1 p1 e to the minus 2t plus c2 p2. For this term, I have a negative. Okay, we know that for e to the minus t, eventually they will go to 0. Okay, so this term goes to 0. we have a C2 e to the 3 minus 3t p2. When t goes to infinity, this term goes to 0, right? There'll be a 0 vector. If C2 is 0, then we just see the first term. If C2 is 0, the first term, that means x1, x becomes C1 P1 e to the minus 5t. And when the t goes to 0, t goes to infinity, C1 e to the minus 5t P1. When t goes to infinity, it is still 0. Similarly, when C1 is 0, then this term, we just prove that they will also go to 0. Okay? So now let's plot. Now we have two vectors P1 and P2. For P1 and P2, suppose this is P1 and here is P2. Okay. Suppose I have an initial value here, x of 0. How do they go? They'll go up or go where? Because we know that when t goes to infinity, they will go to 0. Okay. So they will go to 0. Suppose if initial value is on P1, it's on P1, like here, okay? Then when t goes to infinity, they'll also shrink to 0. They will go to 0. Similarly, as long as you are in the line in the direction of P1, they will go to 0. Here, if you lie on the vector of P2 in the beginning, they will also go to 0. Here is your initial starting point. And since whatever your initial position is, eventually they'll go to 0. So for this point 0, 0, we say this is 0, 0. The origin is called stable attractor point. Okay. This is based on two different eigenvalues, and they are real and negative. What if they are repeated and also negative? That'll be the next one. If they are repeated, say they are all minus 3. For example, lambda 1 equals lambda 2 equals minus 3. Then my solution x is c1 p1 e to the minus 3t. The second one, since they are repeated, remember, I still have e to the minus 3t. And when t goes to infinity, I have c1 p1 plus c2 p2 e to the minus 3t. Then that's a zero vector, because this is the initial point. Okay, so in this case, if I have initial point here, here, even here, then their trajectory, they'll eventually go to 0. And in this is also a stable point. So 0, 0 is stable attractor point. All right. What if the eigenvalues are greater than 0? You have exponential like e to the 5t, e to the 10t. Then you expect finally the trajectory will go to infinity. So here, if eigenvalues are real and positive and they are distinct, we still use 5 and 3 as an example. Lambda 1 is 5, lambda 3 is 3. Then my x, c1 p1 e to the 5t and p2 with e to the 3t. When I take the limit and then t goes to infinity, we take the common terms outside, say e to the 5t outside. Have c1 p1 plus c2 p2 e to the minus 2t. For this term, okay, for this term, there goes to 0 because it's the exponential minus term. So this one you will see that they'll go to 0. Then I have the first part. For the first part, when t goes to infinity, c1 e to the 5t p1. Then this will be going to plus infinity or minus infinity. They will go to infinity. We need to consider two terms separately. Okay, so first here, this go to 0, and for considering p1, this vector, they still go to infinity. Now if I just consider the second one with that c1 0, If C1 is 0, then I only have C2. And in this case, when I take the limit when t goes and that the t goes to infinity, I have C2 P2 e to the 3t. So they will also go to infinity. In this case, your trajectory first, this is still P1, here P2. Then they will go to infinity. Okay, suppose this is the initial value or position x of 0. In this case, the origin, you see that they cannot just cross to the origin. The origin becomes an unstable point. So we call this origin 0, 0 is unstable, repelling point. When two eigenvalues are repeated, they are the same, but they all greater than 0. Let's take 3 as an example. Lambda 1 equals lambda 2 equals 3. Then my answer x is C1 P1 e to the 3t plus C2 P2 e to the 3t. When t goes to infinity, I have a C1 P1 plus C2 P2 e to the 3t. And again, that this part is the initial value. So this becomes e to the 3t times initial value. That will be infinity. So in this case, so if my initial point is here, they will just go straight to the infinity. And this is also called, the origin is also called unstable repelling point. Okay. Any questions so far? Now we just mentioned two eigenvalues are negative or all eigenvalues are positive. Those situations. But what if I have one eigenvalue greater than 0 and one eigenvalue less than 0? For example, like eigenvalue 1 is negative, eigenvalue 2 is positive. Then my solution is C1 P1 e to the minus 3t plus C2 P2 e to the 5t. When I let t goes to infinity, I have a C1 P1 e to the minus 3t plus C2 P2 e to the 5t. This one goes to 0, okay. But the second part for C2, no, because it's 5t, then we'll go to infinity. If C2 is 0, then I only have the P1, this direction. Then you can see t goes to infinity, C1 P1 e to the minus 3t. That should be 0. Oh, here again, this is P1, this is P2. And then for P2, P2 is here. Okay, they will go to infinity. So if they're on this direction, they'll go to infinity. Go to infinity. Go to infinity. But if you are in P1, they'll go to 0. And the origin is called saddle point. Now, we just consider all the possibilities of the eigenvalues as a real and also positive or negative. What if the eigenvalues are not real values? They are complex numbers. First, it's just pure imaginary eigenvalues. Lambda 1 equals I beta, and if we have the conjugate, I mean if I have the complex numbers for the eigenvalues, they should be in pair. Okay, I have I beta, then I expect another eigenvalue should be minus I beta, the conjugate of your first eigenvalue. So if they are pure imaginary eigenvalues, then what happens to this? So suppose, for example, if I have x prom equals 0, minus 1, 1, 0, x, my eigenvalue lambda 1 is I, and I can find my eigenvector 1, I, eigenvalue minus I, their associated eigenvector 1 minus I. Then your x should be C1 P1 e to the lambda 1t plus C2 P2 e to the lambda 2t. So C1 1I e to the lambda 1t plus C2 P2 1 minus I e to the lambda or minus I. I know lambda 1, so it should be IT minus IT. So it is C1 e to the IT plus C2 e to the minus IT. Second row, I C1 e to the IT minus I C2 e to the minus IT. What is the e to the IT? Use the Euler formula. Okay. Use the Euler formula. I have C1 cosine t plus I sine t. I C1 here, e to the IT is same thing, cosine t plus I sine t. Oh, plus C2 cosine t minus I sine t. Here minus I C2 cosine t minus I sine t. Rearrange this. So C1, I have cosine t. C1 times cosine t, C2 times cosine t. So it will be C1 plus C2 cosine t. And here C1 minus C2 times I sine t. So C1, C2 are the constants. So I can have it as a K1. C1 plus C2 is still a constant. So I just combine that and give that the name, another name called K1. And C1 minus C2 becomes K2. So this, I can take the magnitude outside as K1 squared plus K2 squared. If I take this term outside, then I have to divide it in the matrix. K1 squared plus K2 squared cosine t. I think I just copied. Save the time. Change something. Here should be minus. Here should be 1. So for the first row, this expression is, I can write it as K1 squared plus K2 squared. The first one is sine theta plus t. Second one is cosine theta plus t, not I. So your x1 is the magnitude K1 plus K1 squared plus K2 squared times sine theta plus t. X2 will be cosine theta plus t. And your x1 squared plus x2 squared will become k1 squared plus k2 squared. So x1 is k1 squared plus k2 squared cosine pi over 2 minus theta minus t. And we can say this is an alpha. Let's just draw this. You can see that this is just like a rotation. Let's plot this first. It's like an inner circle. Okay, and here we have the angle alpha and x. Suppose x of 0 initial value is here. So in this case, if it is pure imaginary eigenvalues, they will just go around this circle. And the radius is a norm of your x in the initial position. Can you say it is stable or not? But they just move around in a circle. So we call this origin is marginally stable point. For the face portrait, we have the last one. If your eigenvalues are complex numbers, and we have the real part and also imaginary part. For example, x prime equals this matrix times A. Okay, this is A matrix. And then we can find the eigenvalues. You can see that the eigenvalues are always like kind of like pairs. I have a 2 plus 3i, and definitely I will expect another eigenvalue, 2 minus 3i. Similarly, for the eigenvectors, if you find one is 1i, the other one should be 1 and minus I. They are like a conjugate. So your x can be expressed as here. This is your eigenvector. Eigenvector times your e to the eigenvalue times t. And also the other one. Okay, so you just bring this back. And then you can rearrange it. Take e to the 2t outside. And then you can write it down, the x, this x as x1, x2. Okay, so let's see what is x1 and x2. Okay, we will combine c1 and c2. And finally, because they are just constants, and in the end, you have the square root of this constant, e to the 2t. And because using the Euler formula, here we have sine theta plus 3t. And the second one is cosine theta plus 3t. And x1 squared plus x2 squared is k1 squared plus k2 squared e to the 4t. So it is k1 squared plus k2 squared e to the 2t, the perfect square. Then we can plot this. So they will go out. Because you can see that there's an e to the 2t. Finally, they will diverge. And for 0, 0, we say the origin is unstable point. And this is unstable spiral point. And since we have e to the 2t for both x1 and x2, so you see this is kind of like a circle and going spiral outside. If x1 is k1 squared plus k2 squared, here we have e to the 2t sine theta plus 3t. But x2 is e to the 3t. Their exponent is different, cosine theta plus 3t. Then this becomes x1 squared, x2 squared. The shape becomes oval or ellipse. But eventually, they will go outside because they will diverge. So later on, when you take the advanced control theory or nonlinear control theory or system, you will see this phase portrait a lot, and you will analyze the system to check if this is stable or not stable. But if it is stable, what kind of stable or unstable term you will have. And that is the last part for this course in this semester.